Okay. So I'm going to just start this with the time. So thank you very much for giving me the opportunity to talk about this research project, which utilizes quasars, or more in general, active galactic nuclei as standardizable candles to measure cosmological parameters. This project started actually forehand with Guido Risaliti. So it was Guido Risaliti and I. Now the group started to expand, and we have now many people working with us. I'm just naming a few, and I'm going to present results from them. So before going into these results, I just want to provide an overview on what is the state of the art, or what was the current background on quasars in cosmology. And first, if we want to use, and this is quite obvious, but just to repeat, if we want to use an astrophysical object for cosmology, this object must fulfill two main properties, among others, but these are just the two main. We need to determine their distance through absolute emission or the intrinsic emission, if we have a way to do that. And it must be observable over a wide redshift range. Regarding quasars or active galactic nuclei, these are very luminous objects. Therefore, for the latter property, there is no problem, because they can be observed up to redshift 7.5, for instance. So no issue with that. Yet, their emission varies across the entire electromagnetic spectrum. And I want to show you this plot. This is a collection of quasars from the Sloan Digital Sky Survey with X-ray data. Here, I don't know if I should be, I don't know. Well, anyway, with X-ray data on the right hand, and the different colors correspond to different photometric bands, and you can clearly appreciate the extent of variability. I mean, the zoology of active galactic nuclei in their population. So how we can use these sources for cosmology? And well, besides the variability, or the fact that the active galactic nuclei comes in a very different shape, I would say, this never stop people from trying. And I'm listing here a few examples. This is not a comprehensive list, I'm sorry, but this is not an actual review, but I'm just listing a few attempts that use quasar. The first is the Baldwin effect. So as soon as the correlation, the anti-correlation between the equivalent width of emission line and continuum was discovered, immediately people start thinking that quasar can actually use in cosmology through this relation. Unfortunately, this relation is affected by high dispersion, and by high dispersion, I'm talking about 0.5, 0.6x. And it's just too high to use this relation currently in a sensible way. There are other techniques that have been proposed, for instance, quasars light curves, but it's extremely time-consuming, telescope time-consuming, or the radius luminosity relation here. For this technique, reverberation mapping data are required, and again, it is extremely time-consuming, and moreover, it is forced to lie a low redshift. So you lose the fact that you can use quasars or active galactic nuclei up to high redshifts. Another technique is the X-ray variability luminosity relation. Is quite promising, although it is not applied yet to data, only in simulations. The quasar radiating close to the Eddington limit, so very bright quasars that are radiating at the Eddington luminosities. I'm also citing the time delays in lens quasar, although this is a rather different way to use quasars in cosmology, because what I'm listing above is just using a relation in a similar way as it is philosophically done with type 1a supernovae. And the last this is what I'm actually going to talk about, is the X-ray to UV flux relation. So I'm going to focus from now on this relation, and I'm going to introduce it first. So here I'm showing the relation between the X-ray luminosity at the 2 kV energy, the monochromatic X-ray luminosity at 2 kV energy, as a function of the UV luminosity monochromatic at 2500 angstrom. The slope of the relation is roughly 0.6, and it is non-linear. It is linear in the logarithmic space. But I want to make a point that this relation is not new. This relation is known since the 80s, so we haven't discovered anything yet. This is something that is very well known within the X-ray community. It has been used several times, especially through the alpha wax index, which I'm not going to talk about. And so nothing new so far. The data that you see there is our latest compilation of sample of quasars, 2400 quasars that we published 3 years ago now. We are planning to expand further the sample, but I'm going to show the results from this one. Is a compilation of data from different data sets. I'm not going to go into the details. What I'm going to say is that the dispersion by using this sample is on the order of 0.24 DEX. And this is currently the tightest relation that is empirically observed in quasars between two quantities, like in this case, luminosities. Now, this is recent actually, because even this relation was affected by high dispersion. What we did was to select homogeneous sample of quasars that are, let's say, homogeneous at both UV and X-rays energies. What do I mean? So the physics behind these relations, so why, for instance, these two quantities are correlated. We do not know the details of the physics behind this. I'm going to just to provide you a phenomenological overview of that. So the UV luminosity is coming from the accretion disk, while the X-ray emission is coming from a plasma that is content scattering the photons coming from the disk, which will re-emit at the X-ray energies. And what I mean by homogeneous is that what I look for the data, for the quasar in order to be used for cosmology is beautiful spectra in the UV where there is no sign of absorption, bright, steep power loss with, of course, emission lines superimposed, and at the X-ray energies, again, power loss with the photon index, which is the slope of this spectrum, which are on the order of 1.9. But there is a range of that when we select the sample. Now, all the details are in the paper that I just that I'm citing here. But the main point is here: if we have a direct view towards the center, so we can pinpoint both the UV and the X-ray emission in quasars, then we can use them for cosmology. Any kind of external contribution is we need to correct or either neglect these sources. How we can use this relation? Of course, luminosities are forbidden. So we go through fluxes. And if you just follow the math, it's very simple algebra. You recover the luminosity distance because fluxes and luminosities, of course, there is a 4 pi d square term in the equation. And as you can see here, this equation is depends upon observables, which we can measure. And we can use these Fx to FUV relation to provide an independent measurement of the AGN distances. So this is what we did. And we can compute then the distance modulus as a function of redshift. The redshift comes from the spectrum. The distance modulus comes from the equation that I've just shown, and we can compile the Hubble diagram in a similar fashion as it is done for type 1a supernovae. So here I'm showing the same compilation that I showed before, where with including also type 1a supernovae, the Pantheon sample. This is not the latest, the Pantheon Plus, but that's fine. And you can clearly appreciate that quasars can extend the distances to a redshift values that maybe probably redshift 2, 3 would be reached by Roman, but redshift 4, 5, 6 will be hardly be probed by any type 1a supernovae. So the combination, the power of it is that we can combine type 1a supernovae and quasars in a similar way. So what I'm showing here is one of our main results when analyzing this Hubble diagram. I'm going to guide you through. So the, as I say, the colored symbols is the sample that I showed you before. Type 1a supernovae are there in magenta. And the dashed line is a fit, assuming a flat lambda CDM model of all of the data that are below redshift 1.5. And then the dashed line is the extrapolation of that. The red line is instead the fit of the entire data set, quasars plus type 1a supernovae, but not assuming any cosmological model using a cosmographic approach. Now, I cannot go into the details. This is just a polynomial expansion in one of the 1 plus z factor. But you can clearly see already from this plot that there is a deviation from the lambda CDM model that is emerging only at high redshift with a statistical significance beyond 3 sigma. Now, 3 sigma is not as high, but I'm going to show you a more quantitative way to show this. So Giada Bargiacchi was a former student of ours. She did the master thesis with us. She's now doing her PhD at the Scuola Meridionale Superiore in Naples. And she published recently this paper where she explored with the data set that I've shown, with the quasar data set that I've just shown, including also baryonic acoustic oscillations and type 1a supernovae, here with several cosmological models. Here I'm just showing one of them, which is the one of the most popular, the flat CPL. So with the equation of state of dark energy that goes like a power law. And you can see from the plot that the blue contours, so these are 1, 2, and 3 sigma, the green data point over there. I don't know why this is not pointed. What should I do? Well, anyway. The green data point is just marking -1 and that should be, well, -1 in W0 in the plot. And both the left and the right graph is showing you that type 1a supernovae and quasars deviates from the expectations or from the results from baryonic acoustic oscillations in particular. We also included baryonic acoustic oscillation in the analysis, and the discrepancy is still beyond 2 sigma. So what it means that within this model, so I'm assuming a model here. So within this model, supernovae and quasar are in favor or of a phantom behavior. Do I believe that this is actually what is happening? Maybe, maybe not, but I'm going to say this again. These results is within this model. And now we are working on analyzing the same data sets with other different models to see whether these values can be actually retrieved, or we can sort of alleviate this. So We also tested these by selecting the sample in different ways, excluding the low redshift, dividing the sample in different photon indexes values, but still we do see that all the results are always consistent. This is the WAW0 plane, and as you can see, there is no difference, regardless the selection that we make. What I'm going to say here is that these, in order to validate, I mean, I would really like to see an independent test that shows that this deviation, this flattening of the Hubble diagram is happening also with type 1a supernovae, but more type 1a supernovae must be observed beyond redshift 1.5. And I bet that they will confirm the deviation. Now I can move on showing other models, but I will stop here and I will use the rest of my time just to show you that we did all the possible tests to verify that we are minimizing any source of bias and systematic in the sample selection, for instance. And first and foremost, I like this plot very much because when we started to do this, to follow this research path, we always check the cross calibration with type 1a supernovae. So between type 1a supernovae and quasars. And there is always an excellent agreement in the common redshift range, which is reassuring. We always test that the slope of the FX FUV relation in narrow redshift range, in narrow redshift bands, is constant across a wide redshift range, and it is actually the values are written above, so it is actually very well consistent with a value of 0.6 across up to redshift 4, for which we have a statistical sample that we can carry on the analysis of this the redshift evolution. So no redshift evolution of the slope of the relation. The sample at high redshift is different from the low AGN analogs, and the answer is no, because it's we analyzed all the quasars one by one beyond redshift 2.5, both at the UV and the X-ray energies, and the stack that you see on the right side of this of my slide are very well consistent with a photon index, which is roughly 2, which is being observed typically in unobscured active galactic nuclei, and the stack of all the high redshift quasars is very well in agreement with the low redshift 1. Moreover, if we do a one-to-one analysis, we can lower the dispersion further between the X-ray flux and the UV flux. So we also asked the question whether we have a differential reddening, or a differential reddening is required in order to explain the discrepancy. And so this is the same Hubble diagram, and we average it in sort of redshift bands that you see with different colors. And we ask, what is the color excess required in order to explain the discrepancy? And the average color excess or dust reddening required is on the order of 0.1 for all the high redshift quasar, which is not realistic at all. We have performed other tests regarding the dust intrinsic reddening, and we always find intrinsic dust reddening lower than 0.02, which is what we expect given the selection. And also, and for the low redshift, we do not see any contamination or very low contamination from the host galaxy. So all these results will be hopefully soon on the RC, but this is a work that is carrying out our PhD student, Bartolomeo Treffoloni. And as I said, we did all possible tests. I'm skipping this because I'm running out of time, and I'm gonna just show that the future for this project lies within the eROSITA and Euclid at the moment. So the combination of the two is crucial. The eROSITA, which is now off due to the war, but the sample that easily that will be observing at the when the survey will be close to end is lower than Redshift 2, but the statistics is such that we will cross-calibrate quasar and type 1a supernova with very high accuracy. And Euclid will observe the statistics of high redshift quasars that are expected to be observed this Euclid is such that I'm very looking forward to the data to play with. So I'm leaving you with my take-home messages. So unfortunately, we do not have an adequate physical model able to explain this empirical relation, and the dispersion of the quasar-Hubble diagram is still too high. But we did perform lots of tests to reassure ourselves and the community that we are doing our best to minimize bias and systematics. And here is just a list of them.